Chapter 3. On the relation between electricity and magnetism. In the preceding chapter, I have given some of the newest speculations in regard to the nature of electricity. The particular views there expressed are not essential to the development of the conception of electric oscillations and electric waves, so that the reader may be skeptical about the atomic structure of electricity and still be able to follow the arguments for Maxwell's theory. In the present chapter, I wish to return to surer ground and give some of the older experiments on electricity and magnetism and on the relation of electricity to magnetism. Prior to 1820, the phenomena of electricity and magnetism were not known to be related to each other. The familiar facts about magnetism were that there is a mineral called lodestone that has the power of attracting pieces of iron, that a piece of soft iron brought near the lodestone becomes also a magnet with the power to attract iron, but only temporarily, for the piece of soft iron loses most of its magnetism when it is removed to a distance from the lodestone, while a piece of hardened steel brought near the lodestone or another magnet becomes a so-called permanent magnet and retains a considerable part of its magnetism even when at a great distance from the lodestone. It was also known that a steel needle, magnetized by rubbing it on a lodestone or another magnet, and pivoted so as to be free to rotate in a horizontal plane, points in approximately a north and south direction. About electricity, it was known that amber, glass, and sealing wax were capable of being electrified by rubbing them with silk, flannel, fur, etc., that the electrifications so produced were of two kinds, positive and negative, that unlike charges attract each other and like charges repel, that these positive and negative charges could be stored in an apparatus in the form of a Leyden jar, and that metals, such as metals, carbon, water, and other conductors could be electrified so that the electricity would readily flow through such substances, and the galvanic cell was known. This continuous flow of electricity in a wire or other conductor is an electric current, and was known to produce heating of the conductor through which it flows. In 1820, a new impetus was given to a study of electricity and magnetism by the discovery by Hans Christian Ørsted of Copenhagen that magnetism and electricity are interrelated. This discovery and some of its consequences is described in the succeeding paragraphs. On the production of a magnetic field by a current of electricity. Ørsted's discovery was nothing less than the important fact that when a pivoted magnetic needle is placed near a wire carrying a current of electricity, the magnetic needle tends to set itself at right angles to the wire which carries the electric current. If the current is reversed, the direction of the deflection of the magnetic needle is reversed. If the wire carrying the current is moved from a position below the needle to a position above the needle, the deflection of the needle is again reversed. Ørsted's discovery has been utilized in the construction of the galvanometer, which is a very delicate instrument for detecting and measuring small electric currents. The principle of the galvanometer is as follows. A magnetic needle pivoted as in the ordinary compass so as to be free to move in a horizontal plane will, if undisturbed, take up a position in the magnetic meridian of the Earth. That is, the needle will point approximately north and south, as in Figure 5. Suppose now that a wire is passed alternately above and below the needle several times so as to form a coil, as shown in Figure 5, with its windings in the plane of the magnetic meridian. Let a current be passed through the coil so as to flow north above the needle and south below it, the north current above the needle and the south current below it. Both tend to deflect the north-seeking end of the magnetic needle to the west, so that the effect of the current on the needle is multiplied by the combined action of the several turns of the conductor around the needle. For a highly sensitive galvanometer, the magnetic needle, instead of being pivoted, is delicately suspended by a fine fiber of spun quartz. In addition to its application to the construction of the galvanometer, Ørsted's principle is utilized in the construction of almost every kind of electromagnetic device. Interpretation of Ørsted's experiment. The results of Ørsted's experiment are now usually expressed by saying that a current of electricity in a conductor produces a field of magnetic force in the neighborhood of the conductor. In explanation of this statement, the reader is asked to recall the familiar experiment in which a sheet of paper laid upon a bar magnet is covered with iron filings. The filings become magnetized and arrange themselves in curved lines stretching from one pole of the magnet to the other, as shown in Figure 6. The direction of these lines, traced by the filings, is approximately the direction of the magnetic force about the magnet. These lines, delineated by the filings, are the lines along which a small suspended magnetic needle would orient itself if brought near the bar magnet. The region in which such a magnetic force exists is called a field of magnetic force. A piece of unmagnetized steel, when placed in such a field, becomes magnetized and retains some of its magnetism even after it is removed from the field of magnetic force. To show the form of the field of magnetic force about a wire carrying a current, as in Ørsted's experiment, iron filings may also be used with the results given in figures 7, 8, and 9. Figure 7 is obtained with a straight conductor running perpendicular to the plane of the paper on which the filings are disposed. The picture shows that when a current of electricity is sent through the straight conductor, the lines of magnetic force are circles around the conductor. The magnetic force is stronger near the conductor and weaker at a distance from the conductor. Figure 8 is obtained with a coil of a few turns of wire. Figure 9 shows the magnetic field produced by a long helical coil called a solenoid. With the solenoid, the field of magnetic force is seen to be remarkably like that obtained with the bar magnet. It may be observed that in the case of each of the coils, the lines of magnetic force depicted by the filings interlink with the electric current. This conception of a field of magnetic force about a conductor carrying an electric current is of fundamental importance in the study of electric waves, in which the action in the medium rather than the action in the wires is the chief factor to be reckoned with. So long as the electric current in the conductor remains steady, the magnetic field remains steady. With changes in the electric current, the magnetic field changes. This changing magnetic field about a conductor carrying an oscillatory current will later be shown to be one of the components of the electric waves produced at the sending station of a wireless telegraph system. On the production of an electric current by a variation of the magnetic field. Bearing in mind that an electric current produces a field of magnetic force about it, let us turn now to the question whether an electric current can be produced by the action of a magnetic field. For a period of 10 years succeeding Ørsted's discovery, experiments directed to this question gave the answer in the negative. Finally, in 1831, Faraday in England and Joseph Henry in America succeeded, almost simultaneously, in obtaining electric currents by the action of a magnetic field and in explaining the cause of previous failures. Faraday and Henry showed that an electric current in a conductor in a magnetic field is obtained as the result of a change in the magnetic field, whereas the previous experiments had sought to produce the effect by the magnetic field in a steady state. One way of producing the required change of magnetic field in the neighborhood of the electric circuit is by the motion of a permanent magnet with its accompanying field toward or away from the circuit. This was done in some of Faraday's and Henry's experiments and is here described with the aid of figure 10. A coil of wire, labeled C, is connected to a galvanometer G. When the north pole of the magnet NS is made to approach and enter the coil C, the needle of the galvanometer is deflected, showing that an electric current is produced. The current is, however, only transient, and after the magnet NS has arrived at its final position and ceased to move, the needle of the galvanometer comes back to its zero position, showing that the current has subsided. Now, however long the magnet NS is left stationary within the coil C, no current is produced, but if the magnet is quickly withdrawn, the galvanometer registers a current in the direction opposite to the current obtained by the introduction of the magnet. This current is also transient and subsides when the magnet NS becomes stationary. If the south pole of the same magnet is now introduced into the coil, the galvanometer shows a transient current opposite to that produced by its own introduction and in the same direction as that given by the introduction of the north pole. Another way of obtaining a similar result is to employ two coils of wire placed near each other but not electrically connected, as shown in figure 11. One of these coils, labeled S, which we will call the secondary, is connected with the galvanometer G, while the other, called the primary P, may be connected with the terminals of a galvanic battery B. No current is shown in the galvanometer when a constant current is sent through the primary. But when the current in the primary is made, broken, or reversed, transient currents are obtained in the galvanometer. That is to say, the current in the primary sets up a magnetic field linking with the secondary circuit. While the primary current is steady, this field is steady, and no effect is obtained in the secondary. But variations of the current in the primary cause variations of the magnetic field and consequently currents in the secondary. The variable currents in the secondary are said to be induced by the variable currents in the primary, and the phenomenon is referred to as electromagnetic induction. It is in part by action of this kind that currents at the receiving station of a wireless telegraph system are produced by the action of variable currents at the sending station. The extension of the effects of electromagnetic induction to the case of two circuits widely separated from each other we shall see to be the result of the use of extremely rapid electric oscillations at the sending station. On mutual induction, let us examine a little more specifically the case of electromagnetic induction described in the galvanometer experiment just above. It was observed that when the current in the primary coil is increasing, the current induced in the secondary coil is in the opposite direction to the primary current. While, if the current in the primary is decreasing, the current in the secondary is in the same direction as the primary current. Perhaps it would be better to speak of the electromotive force in the secondary rather than the current, because the electromotive force in the secondary bears a simple relation to the current in the primary. The simple relation is that the electromotive force in the secondary is proportional to the time rate of change of the current in the primary. If E sub S is the electromotive force induced in the secondary, and I sub P the current in the primary, and I dot the time rate of increase of the current I sub P, then theory and experiment show that E sub S equals negative M times I dot. This is equation 1. In this equation, M is a constant depending on the form and position of the two circuits. M is called the coefficient of mutual induction, or more briefly, the mutual inductance of the two circuits. M is found to have the same value if the variable current is sent through the secondary and the electromotive force consistent with the above the primary. The mutual inductance of two circuits is defined as the electromotive force induced in one of the circuits when the current in the other is changing at the rate of 1 unit current per second. The mutual inductance between two circuits is increased by increasing the number of turns on either or both of the circuits, or by bringing the circuits nearer together, or by introducing iron or other magnetizable metals within the circuits. Methods of calculating the mutual inductance of circuits of various forms are given in Appendix 2. By a reference to equation 1 given above, it is seen that the electromotive force induced in the secondary is increased by increasing the rate of change of current in the primary. That is, in order to get as large an induced electromotive force at our receiving station, we should have as large a current as possible at our sending station and change it as rapidly as possible. This result is best attained by the use of currents of high frequency at the sending station, such as are obtained by the discharge of a condenser. On self-induction. Let us now see what occurs when the current in a circuit is varied. In this case, the secondary previously considered is dispensed with, and the variation of current in the circuit produces a changing magnetic field about the circuit itself. This action, tending to oppose the variation of the current in the circuit, is called self-induction. The back electromotive force due to self-induction in the circuit is connected with the current in the circuit by the formula E sub I equals negative L times I dot. This is equation 2, in which L is called the coefficient of self-induction, or more briefly, the self-inductance of the circuit. I dot is an abbreviation for the time rate of change of the current. The subscripts 1 show that all the quantities refer to the same circuit. Consistent with equation 2, the self-inductance of a circuit may be defined as the back electromotive force of induction in the circuit when the current in the circuit is changing at the rate of 1 unit current per second. The numerical value of the self-inductance depends on the geometrical form of the circuit. In Appendix 2, formulas are given for calculating the self-inductance of some simple forms of circuit. This discussion of self-inductance is here introduced in quantitative terms because this quantity is of fundamental importance in the study of oscillatory currents. I am aware that the semi-mathematical form in which the idea is presented may fail to give a clear conception of the phenomenon, so I propose to attempt in the next chapter to describe self-induction by the aid of certain familiar analogies. Chapter 4. On the resemblance of self-induction to mechanical inertia. In the previous chapter, it has been pointed out that self-induction is the action of a variable current on itself due to the production of a variable magnetic field by the current. When a current of electricity flows in a circuit of any form, a field of magnetic force is set up and links with the circuit. The manner in which the flow of current in the wire produces magnetic effects in the surrounding medium is not completely understood, but that such effects exist is made evident by bringing a magnetic compass needle up near the circuit. The compass needle tends to set itself in certain intangible lines called lines of magnetic force. The lines of magnetic force produced by a current are closed curves linking with the wire carrying the current, as is shown by the compass needle, or by the distribution of the iron filings depicted in figures 7, 8, and 9. Experiments similar to those cited in the previous chapter show that when a change is made in the electric current in the wire, the magnetic field linking with the wire is changed, and that these changes in the magnetic field impress back upon the circuit an electromotive force opposing the change of current. The self-induction of an electric circuit may thus be described as a property that tends to prevent a change of the electric current in the circuit. In this respect, self-induction resembles the property of inertia in matter. The The inertia of a body is that property by virtue of which a body tends to persist in its state of rest or motion. If a body is at rest or is moving with a given velocity, the inertia of the body opposes a change of its state of rest or motion. In a similar manner, the self-induction in an electric circuit opposes a change of the electric current in the circuit. From this, it is not to be inferred that electricity itself is a form of matter possessing inertia, because in the case of the electric current, we may believe that the inertia resides primarily not in the electricity, but in the magnetic field set up by the current. The correctness of this belief is evidenced by the fact that with a fixed current flowing in a wire, the self-induction may be greatly increased by bending the wire into the form of a coil. Now, making the wire into a coil does not change the amount of electricity flowing in the wire, but it does change the strength of the magnetic field about the wire. The inertia of the current, therefore, has its existence not primarily in the conductor, but in the medium surrounding the conductor. The contrast of self-induction with resistance and its resemblance to inertia. The self-induction of a circuit acts upon the current in a manner entirely different from the manner in which resistance acts. The resistance of a circuit always opposes the flow of the current, and when a current is sent through a conductor, some of the energy of the current is used up in overcoming the resistance of the conductor, or, more properly speaking, some of the electric energy is converted into heat. This is true whether the current is increasing or diminishing or is steady, and the heat developed is not again completely available for producing electric current, so that a continuous supply of energy is needed at the source of the electric current to keep up the current against the resistance of the circuit. Self-induction, on the other hand, does not change the electrical energy into heat. When the current is steady, self-induction has no effect. If, however, the current is increased, then some of the energy supplied to the system is employed in establishing the magnetic field. If now the current is allowed to decrease by an equal amount, the energy stored up in the magnetic field is restored to the conductor and helps to maintain the current. Thus, during a cycle of change of the current, as much energy may be obtained from the magnetic field as was given to it. Hence, if we have an oscillatory current in a circuit, none of the energy of the current is consumed by the action of the self-induction, and the supply of energy at the source is wasted only in overcoming the resistance of the circuit. It is apparent that in respect to the consumption of energy, self-induction resembles inertia in matter. Energy is required in order to set a heavy body in motion, but this energy is recovered when the body is stopped, and the only loss of availability of energy in a cyclic process in which a body is started in motion and stopped again is that lost in overcoming friction in the machinery used for starting and stopping the body. When a body is set in motion, the energy supplied in producing its motion is stored up in the body as kinetic energy, and this analogy has led many writers to refer to the energy of the magnetic field as kinetic in character. Without necessarily committing ourselves to this precise proposition as to the kinetic character of the magnetic field, it will still be useful to keep in mind that self-inductance opposes changes in the electric current in the same general manner as inertia opposes changes in the motion of bodies. Keeping this analogy in mind, we can easily foresee many of the facts about the flow of electricity. For example, suppose that a rapidly alternating electromotive force is applied to a circuit containing a large self-inductance. Usually only a small current will flow, just as only a small motion will generally be communicated to a heavy body by a rapidly varying material force. There are, however, special cases in which the periodic force will set up a large motion of the material body. This happens when the period of the force is the same as the natural period of the body. But in order for the body to have a natural period, something besides inertia is required. Namely, the body must be elastic or must be elastically attached to something. So, in the case of the electric circuit, it is also possible to get a large current with a rapidly varying electromotive force, provided the circuit contains, besides its self-inductance, a suitable amount of electrostatic capacity, which will be shown to supply the factor required to give a periodicity to the electric circuit. Before developing further our notions in regard to self-inductance, it is proposed to introduce this other phenomenon that enters prominently into the discussion of electric waves, namely the phenomenon of electrostatic capacity. Chapter 5, on electrostatic capacity. The last two chapters have been devoted to a discussion of electric currents and the magnetic field accompanying such currents. In order to arrive at a conception of the nature of electric waves, it is necessary also to give some attention to the action of electric charges at rest. This is the subject of electrostatics. Here again, we must look to Faraday for the fundamental discoveries. In the beginning paragraph of his most important research on this subject, Faraday says, To those philosophers who pursue the inquiry zealously yet cautiously, combining experiment with analogy, suspicions of their preconceived notions, paying more respect to fact than to theory, not too hasty to generalize, and above all things, willing at every step to cross-examine their own opinions, both by reasoning and by experiment, no branch of knowledge can afford so fine and ready a field for discovery as this. Influence of intervening medium on electric attraction. The result obtained by Faraday in the research referred to is that electrostatic repulsion or attraction between two charged bodies is influenced by the medium intervening between the charged bodies. If, for example, we have two flat metallic plates placed parallel to each other and we charge one of the plates positively and the other negatively, the electrostatic attraction between the two charges on the plates will be less when the plates are separated by glass than when they are separated by air, provided the plates are charged with the same quantity of electricity in the two cases. The attraction between the charges on the plates with glass intervening will be about 1/6 as much as that with the same thickness of air intervening, so that in order to get the same force between the charges on the plates, in the two cases, we must put upon the plates with glass between them 6 times as much electricity as is required with air between. We thus come to the result that the insulating medium between the oppositely charged metallic plates serves not merely to separate the plates and prevent them from losing their charge, but serves also to determine the charge the plates will receive for a given electromotive force. For example, a given battery connected between the plates. And since the insulating medium between the plates has other functions than merely to insulate, Faraday proposes to designate the insulating medium by the name dielectric when reference is made to the force acting through it. He says, I use the word dielectric to express that substance through or across which the forces are acting. On condensers. The apparatus consisting of two conducting bodies separated by a dielectric is called a condenser. An ordinary Leyden jar consisting of two metallic coatings separated by glass is a familiar case of an electric condenser. Any two conducting bodies with a dielectric between constitute a condenser. As an extreme case, a single conducting body isolated in space is considered a condenser, with empty space as dielectric, and with the other conductor removed to an infinite distance. As another example, a charged body in the neighborhood of the Earth is a condenser, with the Earth for the other conductor and with air as dielectric. Capacity of condenser. Different condensers are said to have different capacities, which term does not refer to the total amount of electricity that the condensers can contain, but to the quantity of electricity they will take under the action of a given electromotive force, namely a unit electromotive force. In the practical system of units, the unit of quantity of electricity is the coulomb, and the unit of capacity, the farad. A farad is the capacity of a condenser that can be given a charge of 1 coulomb under the action of 1 volt of electromotive force. The farad is a very large unit of capacity. For example, the electrostatic capacity of the whole Earth is only about 0.000078 farad. That is to say, it would take only about 7/10,000ths of a coulomb to raise the potential of the Earth 1 volt. Since the farad as a unit is very large, the capacity of a condenser is often designated in millionths of a farad, or microfarads. The quantity of electricity Q on each plate of a condenser of capacity C is given by the relation Q equals C times V, where V is the difference of potential between the plates. Dielectric constant. Returning now to the function of the dielectric in determining the capacity of a condenser, the term dielectric constant of a substance is used to designate the capacity of a condenser with the substance as dielectric relative to the capacity of the same condenser with empty space as dielectric. The dielectric constant of air and all the gases at ordinary pressure is approximately unity. This means that the capacity of a condenser with a gas as dielectric is not much changed when the gas is pumped away. In the example cited above, the dielectric constant of a particular glass is given as 6. That is, the quantity of electricity that a condenser will contain under a given electromotive force with this glass as dielectric is 6 times the quantity the condenser will contain under the same electromotive force when air is substituted for the glass. A table of dielectric constants, together with some numerical formulas for calculating the capacity of some simple forms of condenser and rules for combinations of condensers in series and parallel, is given in Appendix 2. General facts about energy and electromotive force of charged condenser. In order to send a charge of electricity into a condenser, energy is required, but the energy is not converted into heat, as it is in the case of a current of electricity flowing against a resistance. For the energy of the charge may be recovered as electric energy when the condenser is allowed to discharge. In a cyclic process in which a condenser is charged and discharged again, There is no loss of availability of energy in the processes that occur in the condenser. And when a condenser charges and discharges alternately in an oscillatory manner, it is necessary to supply energy from without, only insofar as the electric energy is radiated or is converted into heat in flowing through some resistance in the circuit. It has undoubtedly been observed by the reader that, in respect to energy, this conclusion is quite like that reached for the case of self-induction, where the return of energy to the circuit again and again was secured. Hence, whether the medium of the magnetic field in self-induction or the medium of the dielectric in electrostatic induction, the opposing electromotive force called into play is proportional to the rate of change of the current. That is, the electromotive force opposing the charging of the condenser is proportional to the quantity of electricity Q in the condenser. Numerically, V equals Q over C, and in proper units, V equals Q divided by C, where C is the capacity of the condenser. Mechanical systems analogous to an electrical condenser. One analogy is the charging of a condenser in the act of supplying water to a tall, cylindrical reservoir. The force required to send water into the reservoir against the hydrostatic pressure of the water already in the reservoir is proportional to the height h of water in the reservoir, which is proportional to the amount of water m in the reservoir. Numerically, in suitable units, P equals m over S, where S is the area of cross-section of the reservoir. S may be looked upon as analogous to C. Another analogy to the action of a condenser is found in the forces called into play in the act of compressing an elastic spring. The restoring force F of the spring is proportional to the amount x by which the spring is compressed. Numerically, F equals x times E, where E is the stiffness of the spring. In the case of the condenser, it should be borne in mind that the greater the capacity of the condenser, the less the electromotive force required in order to charge it with a given amount of electricity. In this respect, capacity of the condenser resembles the reciprocal of the stiffness of the spring. For the greater the stiffness of the spring, the greater the force F required to compress it by a given amount. Flow of current in a circuit containing a condenser. The reader will note the following fundamental facts in regard to the action of a condenser. If a battery having a constant electromotive force E has its positive pole connected to one plate of a condenser and its negative pole connected to the other plate, electricity will flow into the condenser and charge it. As the condenser charges, this gives rise to a back electromotive force opposing the flow, so that the current is diminished more and more by the opposing electromotive force of the condenser as the condenser is charging. The electromotive force at each instant is proportional to the quantity of electricity that has already entered and is inversely proportional to the capacity of the condenser. When this opposing electromotive force becomes equal to the electromotive force of the battery, the current ceases. Then E equals Q over C, where Q is the final charge attained by the condenser. After this condition is reached, no further current flows. This process of charging the condenser is described as gradual because time is required for the final condition to be established, but this time is usually very short. Work done in charging condenser. During this process of charging the condenser, the average electromotive force of the condenser was 1/2 E. The work done, which is the charge introduced multiplied by the electromotive force of the condenser, is Q times 1/2 E, or substituting for Q its value E times C, the work W done in charging the condenser is W equals 1/2 EC. Chapter 6. On the discharge of a condenser through an inductance and resistance, the oscillatory discharge. We are now ready to undertake a more critical examination of the proposition set down in the first chapter that, under certain conditions, the discharge of a Leyden jar is oscillatory. As a mechanical analogy, let us consider the motion of a heavy bob attached to an elastic spring, as in Figure 12. If now the bob is pulled down to a position B and released, the spring draws it back again to A. During this process, the bob acquires a velocity determined by the stiffness of the spring and the mass of the bob. When the bob reaches A, the spring ceases to pull, but the bob, by reason of its inertia, moves on up to a position C, during which process the spring is compressed. When the bob has reached C, it has lost its velocity and is now driven back by the compressed spring. In this way, the vibratory motion is kept up for some time and would be kept up indefinitely, but for the fact that the resistance of the air and the imperfect elasticity of the spring convert some of the energy into heat during each excursion, so that the amplitude of the motion is diminished more and more until the body finally comes to rest at A. As another illustration, suppose a body of water to be contained in an upright tube of the form shown in Figure 13. Let the surface of the water in its position of rest be at A and A prime in the two arms of the tube. Suppose now that the water is moved into the position B and B prime and released. The column of water will vibrate back and forth in the tube so that its level in the left-hand arm of the tube comes successively above and below the position A. During each excursion, the amplitude of the motion is diminished till the water finally comes to rest in its initial position. Both of these forms of mechanical vibratory motion are easily realized in practice, and both bear a marked resemblance to the flow of electricity in the discharge of a condenser through an inductance and resistance. In order now to understand how a condenser discharge may be oscillatory in character, suppose a Leyden jar or other form of electrical condenser of capacity C to be initially charged as from an electric machine with a quantity of electricity plus Q on one plate and minus Q on the other. And suppose that the condenser has in series with it a self-inductance L and a spark gap S, as in figure 14. At first, let the spark gap be too wide for the spark to pass. Positive electricity will be distributed over the one coating and one knob of the spark gap, and negative electricity will be distributed over the other coating, the coil L, and the other knob of the spark gap. Let V0 be the difference of potential between the plates of the condenser. Before the current starts, there will be the same difference of potential between the knobs of the spark gap because all parts of a conductor in which no current is flowing are at the same potential. Let us suppose now that the knobs of the spark gap are made to approach each other until the gap is short enough for the potential to start a spark. That is about 30,000 volts to the centimeter if the terminals of the gap are balls 1 centimeter in diameter. When the spark starts, the resistance of the gap suddenly drops to a very small value, in some cases to a small fraction of an ohm, and the condenser discharges itself across the gap under the action of the high electromotive force between the plates. The current flowing through the circuit has a small value when the spark first begins to pass. If it were not for the self-induction of the circuit, the current would spring to a large value because the electromotive force of the circuit is high and its resistance low. We have seen, however, that the self-inductance acts in such a manner as to oppose rapid changes in the current. As a result, the current requires time to attain its maximum. When the current reaches its maximum, the condenser is completely discharged, but there is a large current flowing. This current cannot stop at once, for the self-induction now acts in the reverse direction and opposes the decrease of the current, so that the current continues to flow after the electromotive force of the condenser has become zero. This process charges the condenser oppositely to its original charge, and when the current in this direction ceases, the back electromotive force of the condenser starts the current in the reverse direction. The condenser is again charged in its original direction. The current again reverses, and the process continues for a number of oscillations depending on the resistance, self-inductance, and capacity of the circuit. The essential factors entering into the production of the oscillatory discharge are the self-inductance and the capacity of the circuit, characterized in their actions by the fact that they are out of phase with each other, so that when the effect of the capacity is a maximum, that of the inductance is a minimum, and vice versa. On account of the resistance of the circuit, some of the electrical energy is converted into heat during each flow of current, so that the maximum attained by the current at each oscillation falls lower and lower until the spark ceases. The decrease of the amplitude of the oscillation under the action of the resistance is referred to as damping of the oscillation by the resistance. It will be seen later that the radiation of energy as electric waves acts also in a manner to damp the oscillations. Criterion. In his mathematical investigation of this problem, Sir William Thomson showed that the discharge of a condenser is oscillatory manner described only when the resistance of the circuit does not exceed a certain value relative to the ratio of the self-inductance to the capacity of the circuit. The exact expression of this condition under which the discharge is oscillatory is R squared less than 4L over C, non-oscillatory discharge. If, on the other hand, R squared is greater than 4L over C, Thomson showed that the discharge is unidirectional, that is, no reversal of the sign of the charge takes place. We should have an analogous condition of affairs with the elastic spring used as an illustration if the bob in figure 12 should be submerged in a liquid, provided the liquid should offer sufficient resistance to the passage of the bob through it. Evidently, the amount of resistance required to prevent the oscillation of the bob will increase with increase of the inertia of the bob and with increase of the stiffness of the spring. The former of these corresponds to L and the latter to the reciprocal of C, so that the fact that L over C will occur in the condition for the oscillation or non-oscillation of the electrical system might have been anticipated. In the case of the water column, if the connecting tube EP between the two vertical cylinders in figure 13 is made sufficiently small to offer enough friction, the motion of the water will also be non-oscillatory. This is analogous to the case of the non-oscillatory discharge of the condenser. Mathematical formulas for the discharge of the condenser. Thomson derived the following equations for the current I at any time t, where t is measured in seconds from the time when the discharge begins. Case 1. If r squared is less than 4L over c, I equals 2v naught over the square root of 4L over c minus r squared times e to the negative rt over 2L multiplied by sine of the square root of 4LC minus r squared over 2L times t. This is equation 3. This is the case of the oscillatory discharge. Case 2. If r squared is greater than 4L over c, I equals v naught over L times e to the negative rt over 2L multiplied by the difference of e to the t over t1 minus e to the t over t2. This is equation 4, in which t1 equals 2lc over rc minus the square root of r squared c squared minus 4lc, and t2 equals 2lc over rc plus the square root of r squared c squared minus 4lc. This is the general case of non-oscillatory discharge. Case 3. If r squared equals 4L over c, I equals v naught over L times t multiplied by e to the negative rt over 2L. This is equation 5. This is the critical case in which the discharge is just non-oscillatory. Graphical representation of oscillatory discharges. By the aid of the equations 3, 4, and 5, the current in the condenser circuit at any time can be calculated in any case in which the constants of the circuit and the initial difference of potential of the plates of the condenser are known. But the calculated values so obtained, we can construct a table, in the first column of which we may place the time in convenient fractions of a second, and in the second column we may write the different values of the current corresponding to these different values of the time. There is, however, another method of representing the results, which affords an easier comprehension. This is the graphical method, and consists in constructing a curve on a sheet of squared paper with a scale of time and a scale of current at right angles to each other. As an example of this method of showing results, let us refer to Figure 15, which is a graphical representation of the flow of current in a condenser circuit in which the resistance is supposed to be 0. The horizontal scale through the center of the figure gives the time in millionths of a second. The vertical scale at the left of the figure gives the current. Such a diagram gives the current at any time. For example, when the time is 0, the current is 0. To get the current at 1/1,000,000th of a second, 1 goes out on the horizontal line to 1/1,000,000th second, which is halfway between 0 and 2. And at this point, 1 erects a vertical line which will be seen to cut the curve at a point the same height as 150 amperes on the margin. This is 150 amperes is then the current at that moment. In like manner, at 3/1,000,000th second, the current is seen to be about minus 130 amperes. From this description of the method of interpreting the curves, it will be evident how the curves are drawn. Namely, a table is made of current for different values of time by the aid of formula 3, and then for each value of time plotted horizontally, the corresponding value of current is erected vertically, and through the points so obtained, a smooth curve is drawn. This process resembles the method employed by navigators to show the route of a ship. Each day, or oftener, an observation of latitude and longitude is made, and a point is put on the map at the intersection of the given latitude and longitude, and through the points thus obtained at successive observations, a smooth curve is drawn, which represents the course of the ship, and from which the position of the ship at points intermediate between the observations may also be approximately obtained. Curves showing condenser discharge. The manner in which the discharge of a condenser occurs under different conditions is represented graphically in the curves of figures 15, 16, 17, and 18. In these curves, the time in millionths of a second is plotted horizontally, and the current in amperes is plotted vertically. These curves are calculated from the formulas given on page 31. In all 4 cases, the capacity, self-inductance, and initial potential are the same, namely, C equals 10 to the minus 6 farads, L equals 10 to the minus 4 henries, and V equals 20,000 volts. The only difference between the conditions of the discharge in the 4 cases is the difference in resistance of the circuit through which the discharge occurs. In Figure 15, the resistance is supposed to be 0, and we have as a result what is called an undamped oscillation. The current oscillates back and forth between a positive maximum of 200 amperes and a negative maximum of 200 amperes. In Figure 16, the resistance of the circuit is 10 ohms, and in Figure 17, this resistance is 20 ohms. These 2 curves show how the current is damped by the resistance of the circuit. The curves of Figures 15, 16, and 17 all come under the conditions of Case 1. If, however, the resistance be 200 ohms, we have the condition for the current to be just non-oscillatory, R squared equals 4L over C, and the equation of the curve is then the equation given under Case 3. This kind of discharge is shown in the curve of figure 18. This case has also the same capacity, self-inductance, and initial voltage as the preceding cases, but the current is seen to rise only to about 75 amperes and then gradually to approach zero. If the resistance be made greater than 200 ohms, we have case 2, in which the discharge is also non-oscillatory. A curve representing this case is not given. The form of such a curve is somewhat like that of figure 18, with the exception that the curve does not rise to so great a value and does not approach zero so rapidly as does the curve in figure 18. The period of oscillation. From equation 3 on page 31, it can be shown that the period of a complete oscillation of the current, in case the discharge is oscillatory, is T equals 2 pi times 2 LC over the square root of 4 LC minus R squared. This is equation 6, in which T is the time of a complete oscillation in seconds. L, C, and R are measured in the same set of units, for example, henries, farads, and ohms, respectively. Pi is 3.4 times 16, the ratio of the circumference to the diameter of a circle. Equation 6 is the exact expression for the period, but in most practical cases that occur in the use of electric waves, it is found that the effect of the resistance is inappreciable in its effect on the period. That is, in equation 6, R squared C squared is small in comparison with 4 LC, so that the expression for the time of a complete oscillation simplifies to T equals 2 pi times the square root of LC. This is equation 7. This formula is usually sufficiently accurate. For example, in the case plotted in figure 16, the period of oscillation calculated by equation 7 differs from the exact value obtained from equation 6 by 1/4 of 1%. The various formulas given in this chapter were first obtained mathematically by Sir William Thomson in 1855. In 1859, Feddersen demonstrated the oscillatory character of the discharge by a revolving mirror photograph of the spark, similar to the photograph shown in figure 3 of chapter 1. Since then, all of Thomson's equations have been submitted to careful tests and have been found to be accurate.